Greetings. In the previous two videos, we managed to define our problems, write down the equations, we knew what the initial conditions were, and also we managed to calculate the mass in each section. This was the calculation of properties. We simplified the equations and learned what we have and what we don't have, and we knew that we couldn't calculate heat transfer or work between A and B, and the only equation which didn't include those terms was the first law of thermodynamics that was written for the whole system for A and B together. So what we did, we inserted no values in it, and therefore we managed to calculate the final temperature. A knowledge of the final temperature gave us the final pressure and the final volume of each section. What we want to do now is to draw all the process on a diagram. And that is a very important step just to learn what has happened in between these two cylinders. So if this is a TV diagram, then constant pressure lines would have such a shape. The three pressures that we are concerned with are 200 kilopascals. The other one is 600 kilopascals. And the final is 1000 kilopascals. Initially, A was on 300 degrees C and 200 kilopascals, so it would be a point like this one. This would be A, say the temperature was 300 kelvins, and I would write dimensions here, and this is a specific volume, which is cubic meters per kilograms, and that would be point A. You see, what I have written in blue is air. Okay, it is the lines on the air diagram which I'm interested in. So that is air, just similar to what I did with a saturation line. For the problems which I had saturation line, I just drew the saturation line and the pressure lines that I wanted and the properties on them, which was just water and had nothing to do with our problem. Now I installed my problem over that over those properties. Now I'm doing here also the same. These lines, the blue lines, are all air. And now what I'm doing with green is to install my problem over this diagram. Now, um, the, this is A and in condition 1, initial condition for A. As for B, the temperature is 1000 kelvins and the pressure is 1000 kilopascals, 1 megapascal. So what we have here is the specific volume for A, which is 0.4305, which is the initial specific volume for A, and also a specific volume for B, which is 0.287. 0.287 cubic meters per kilograms. Now, A and B are in equilibrium at its final condition, and therefore our final condition would be a point somewhere in between, the um, somewhere like this one, where the pressure is 600 kilopascals, the temperature is 720 kelvins, 720, the temperature is 720 Kelvin, somewhere in between, and also the specific volume is somewhere in between, which is 0.344 cubic meters per kilogram. So this is our problem on a diagram, which we have drawn, and we know what has happened. The process from A, and this is 2, this is 2, and this is B1. Okay, the process from A1 to 2 would be something like this. We don't exactly know, so it's better if I draw it just not on continuous line, just on dashed lines. And also there has been a problem from B1 to 2, and both have come to this equilibrium at 2. None of the processes is semi-equilibrium. They were fast to start with and then gentle to end with, but still the final point that they come to equilibrium is point 2, where the pressure is 600 kilopascals, the temperature is 720 kelvins, and the specific volume is 0.344 cubic meters per kilograms. Now, there's still another explanation on this problem where we should extend. Look, we have written two equations. This equation shows us how much energy was given to A. You see, B was warmer and had a higher pressure, so B both did work to A and also did heat transfer. A similar point is true for B, since when we talk about B, this is the energy, this is the change of energy in B, and that is both heat transfer and work that is given to A. So these two terms should be similar, since B has given some energy to A. Okay, and the sum of these two terms should be the same, although we don't know. In fact, the heat transfer to A and B is the same, opposite signs, and the work between A and B are the same, but with opposite signs. Now, we can calculate the left-hand side of this equation, and that would be, we can write down MA, CB0 times T2A minus T1A equals Q12A minus W12A. The outcome is 2.323 times 0.717 times 720 minus 300, and that equals Q plus W, and the answer is 700 kilojoules. At the same time, if we do the same for B, it would be MB times CV0 times T2B minus T1B equals Q12B minus W12B, and the outcome is 3.3 484 times 0.717 times 720 minus 1000, and that also equals minus Q and minus W. I have changed the sign just to show that they act in the opposite way. We don't know the values, but still we can know the signs, we know the signs, and we can implement them. And still this one would be minus minus 700, which means that B has lost 700 kilojoules of energy and A has gained 700 kilojoules of energy. How it is divided between heat transfer and work, we just don't know. Still, what we know is that they are equal and no energy has transferred outside this cylinder. Well, uh, the problem is, as I have said at the start, and now I repeat, is a transfer of energy between A and B. The piston would move fast when we draw the pin, and it would move fast to the left towards A, so it is not semi-equilibrium. And the heat transfer also would start fast at the start because there is quite a temperature difference between the two. The boost work and heat transfer would be slower at the end. Heat transfer would take far longer because the heat transfer is a slower process. The pressure waves move at speed of sound. They are faster, but when they come to equilibrium, which would take a very, very long time, they have gone through non-equilibrium process. Okay, thanks very much for watching and cheers.